So next, so I am going to show you the notes for the term power. So in the previous class, I have discussed the term power and I have discussed the calculation of power and some simple situations. So I am going to show you the notes for the same now in this class. That means I am going to show you the notes for what I have discussed about the term power in the previous class. So those who are copying the notes, come on, get ready with your notebook and pen. So I am going to show you the notes on the screen. So those who are writing the notes, they can start writing the notes. So wherever they need more time to copy the notes, they can take a pause and take more time if required. So put the guiding power, the basic formula for power, average power delivered by an agent is equal to work done by the agent divided by time interval. So all this I have already discussed in the previous class. I'm just giving the notes for what I have already discussed in my previous class. So instantaneous power delivered by agent is given by P equal dWA by dt. As explained already in the earlier class about this, I am summarizing the same discussion. dWA represents work done by the agent during the infinitesimally small interval of time dt. dWA can write FA bar dot dr bar. Here FA bar is the force applied by the agent on the body. F bar subscript A represents the force applied by the agent on the body. So P equal FA bar dot V bar. The FA bar is instantaneous force applied by the agent and V bar is instantaneous velocity to the body. Come on, those who are writing the notes, come on, copy down this. So in case you need more time to copy this, you can take a pause and take your own time. Then special cases. Case 1, if a body is moved with uniform velocity V bar due to a constant external force F bar which acts in the direction of motion, and the power delivered by the pulling agent is given by P equal FV. So I am giving the working for this conclusion. The velocity of the body is constant. I mean, when the body moves in a straight line path with uniform velocity, then magnitude of the displacement is given by F equal to Vt and work done by the agent. And the force acts in the direction of the displacement is equal to F into S, so I can write F equal to V into T. So average power delivered by the agent is W by T, FVT by T are equal to P, FPA equal to FV. So in this case, in this special case 1, the average power delivered by the agent for a finite time interval T, during which velocity is uniform, same as the instantaneous power. Then both F bar and V bar are constants. So those who are copying these notes, in case you need more time to copy the notes, you can take a pause wherever required. See the case 2. The constant force F bar applied by the external agent acts at an angle theta with the direction of the motion. The body moves with uniform velocity. And the power delivered by the agent is given by P equal to FV cos theta. Then you can see the working here. V is constant and S equal to V into T. Work done by the agent, you can write Fs cos theta. You can write S equal to V into T. So average power delivered by the agent is equal to work done by agent divided by time interval. So FVT cos theta by T. Or you can write FV cos theta F bar dot V bar. So in this special case 2 also, the average power delivered by agent for a time interval T is same as the instantaneous power at any instant in the time interval T. Come on, those who are writing the notes, finish writing this. So in case you need more time to copy this, you can take a pause and copy the notes. See the case 3. The body starts from rest and moves with a constant acceleration A under the action of a constant external force F bar applied by an external agent. Then the instantaneous power after time t will be double the average power for the time interval t. So I am going to show the calculation for this conclusion. First, if you can finish copying this conclusion. This conclusion is valid when the body starts from rest and moves with constant acceleration under the action of a constant external force F bar applied by the agent. So in case you need more time to copy this, you can take a pause. I'm going to showing the working for this third case. The average power for a time interval t can write W by T. Can write W equal Fs cos theta. The body starts from rest and moves with constant acceleration. Then we can write S equal to half AT square. So you can substitute S equal to half AT square. So average power for time interval t is PA equal half FAT cos theta. So instantaneous power you can write denoted by P subscript I equal dW by dt. Here dW is the work done by the agent during the infinitesimally small interval of time dt. So dW can be written as F bar dot dr bar. Here F bar is the force applied by the agent on the body. Dr bar represents the displacement of the body during the infinitesimally small interval of time dt. Dr bar by dt gives you the instant velocity v bar. So pi you can write F bar dot v bar, or you can write pi equal Fv cos theta, where theta is the angle between F bar and v bar. The acceleration is constant and initial velocity u is 0. Then instant velocity at time t can be written as v equal at. So we can write instantaneous power after time t can be Fat cos theta. So earlier we calculated average power after for a time interval t is half Fat cos theta. Instantaneous power equal to Fat cos theta. Come on, finish writing. In case you need more time to copy this, you can take a pause and take your own time. So you can divide pi with pa, you get Fat cos theta by half Fat cos theta, or pi equal to pa. Come on, finish writing. So in case you need more time to copy the notes, you can take a pause. I'm going to show you the next case. Case 4. So body of mass capital M is lifted through a vertical height h without acceleration in time t. And the power delivered by the agent is given by P equal mgh by t. This formula holds good in the absence of friction and air resistance. That means this formula holds good when the body is lifted in the absence of air resistance and friction and with negligible acceleration or with uniform velocity. I'm going to show the working for this case. Come on, all of you, first finish copying the conclusion. So resultant force acting on the body is lifted vertically upwards, away from surface of ground, can be F minus mg. Here F is the magnitude of the force applied by an external agent which acts in the direction of motion. From Newton's second law, that can be written as m into A. A is the magnitude of the acceleration with which the body is lifted upwards. From this magnitude of the force applied by the agent, when it is lifted vertically upwards with an acceleration A, given by F equal m into G plus A. So the average power delivered by the agent for a time interval T, you can write W by T. So the average power delivered by the agent, you can write P subscript AV equal WA by T. Here WA represents work done by the agent for a time interval T. The force applied by the agent is constant and acts in the direction of the displacement of the body. Work done by the agent for a time T can write F into S. Can write F equal m into G plus A. So if A is 0 and S equal H, that means if the acceleration is 0, I mean the body is lifted with uniform velocity or with negligible acceleration, then you can write A equal to 0. And if it is lifted through a vertical height H, then S equal to H. In that case, P equal to mg H by T. Come on, finish copying this part. So I have already discussed up to here in my previous class regarding power. Come on, finish copying. In case you need more time to copy the notes, you can take a pause and take your own time. Next, I would like to discuss units of power. Probably most of you must be already familiar with these units of power. You might have studied in lower classes. But still I mention once. In unit of power in any system is equal to unit of work in that system divided by unit of time. SI unit of power is watt, SI unit of work is joule. So 1 watt you can write 1 joule per second. So for practical purposes, sometimes the power may be written in kilowatts. 1 kilowatt is 1000 watts or 1000 joules per second. Sometimes power may be, particularly powers of pumps and engines are usually expressed in horsepower. So 1 horsepower can be done as 746 watts. That means 1 horsepower is the power of an agent which works at the rate of 746 joules or 7 per second. So 1 horsepower is the power of an agent which works at the rate of 746 joule per second or 746 watt. Think you finished copying? Next I am going to show you a problem. So horsepower sometimes in short form written as HP. Look at the problem here on the screen. Problem number 2 in work power energy. I will read out the problem first. Next I am going to solve that problem. Block of weight 100 Newton rests on a rough horizontal floor. Nu s equal to 0.5 and nu k equal to 0.4. A horizontal force is applied on the block which is just sufficient to start the block moving. The same force is maintained even after the motion begins. Then find the first part of the question. Average power delivered by the agent in the first 3 seconds. Second part of the question. Average power during the 3rd second of its motion. Third part of the question. Instantaneous power at the end of 3rd second. Take G as 10 meter per second square. Come on. Copy down the information. In case you want to try it on your own first, you can take a pause and try it. But I am going to now discuss this problem. So here, let us draw the free body diagram for the block. The block is initially at rest on a rough horizontal floor. The first external force which acts on the block is its weight mg. Which acts vertically downwards. Then second force on the block is the normal reaction force by the floor. Here N is the magnitude of normal reaction force on the block by surface of floor which acts vertically upwards, perpendicular to surface of floor in contact and directed away from surface of floor. Let capital F denote the magnitude of the horizontal force applied on the block. Let us suppose the acts towards right. So the force of friction on the block by surface of the floor acts towards left side opposing the motion of the block relative to the floor. The force of friction on the block during the motion will be kinetic friction. I choose the horizontal direction, that is the direction of the force applied on the block, positive direction of x-axis, and the vertical upward direction as positive direction of y-axis. The first part of the question you are asked to find average power for 3 seconds. To find the average power for 3 seconds, you have to find the work done by the agent for 3 seconds. That means you have to find work done by the force applied by the agent for 3 seconds. To find the work done by the agent for 3 seconds, you have to first find the displacement covered for the first 3 seconds. To find the displacement covered for the first 3 seconds, you have to find the magnitude of accelerator of the block. To find the magnitude of accelerator of the block, we have to apply Newton's second law. So for that, before that, we have to find magnitude of kinetic friction on the block and magnitude of the horizontal force applied on the block. So in the vertical direction, I choose the vertical upward direction as positive direction of y-axis. So N represents the magnitude of normal reaction force on block by the floor which acts vertically upwards in the positive direction of y-axis. The weight mg of the block acts vertically downwards in the negative direction of y-axis. So net force of the block in the vertical direction or y direction will be equal to N minus mg. But here the block has no motion in the vertical direction. So y component of acceleration is 0 and y component of resultant force of the block is 0. So magnitude of normal reaction of the block by the floor will be equal to m into g. The block, it is given that the horizontal force applied on the block which is just sufficient to start the block moving. The horizontal force applied on the block is just sufficient to start the block moving. And it's given that same force is maintained even after the motion begins. As I discussed earlier in friction, the block is initially at rest on a rough horizontal floor. Then the least horizontal force needed to just start the block moving is equal to magnitude of limiting friction between the two surfaces in contact. So that means the magnitude of the horizontal force applied to the block can be taken to be nearly equal to the magnitude of the limiting friction on block by the floor. Strictly speaking, the block starts moving when the horizontal force applied to the block just exceeds this limiting friction US into N. That means the block starts moving even if the magnitude of the horizontal force applied to the block exceeds this limiting friction by infinitesimally small amount. So according to the problem, the horizontal force applied to the block, which is just sufficient to start the block moving. So therefore, magnitude of the horizontal force applied on the block can be taken as equal to magnitude of limiting friction, that is nu s into n or nu s into mg. But during the motion, the magnitude of kinetic friction acting on the block is denoted by Fk, which is equal to nu k into n. Here n equal to mg. So magnitude of the resultant force on the block along x-axis. When y component resultant force is 0, when resultant of all the force acting on the block, we can write Fx, means x component resultant force. So Newton's second law, that can be equal to mass into acceleration. So here capital F is the magnitude of the horizontal force applied on the block by the external agent, which acts in the direction of the motion of the block. And Fk represents the magnitude of kinetic friction of the block, which acts opposite direction of the motion of the block. So magnitude of the resultant force of the block along x-axis F minus Fk. From Newton's second law, this will be equal to product of its mass and acceleration. So you can substitute here F equal to nu s mg on the left side, and Fk equal to nu k into mg. So nu s mg minus nu k into mg equal to mga. Or magnitude of the acceleration of the block is equal to nu s minus nu k into g. Actually, this calculation I have already discussed in the past in one of the special cases in friction. The first special case in friction. That means if horizontal force applied on the block when it is initially at rest on rough horizontal floor, which is just sufficient to start the block moving, and if the same force is maintained even after the motion begins, then magnitude of the acceleration of the block is given by A equal to nu s minus nu k into g. Here nu s is given to 0.5, nu k is given to be 0.4, g is given to be 10 meter per second square. So you get magnitude of the acceleration of the block equal to 1 meter per second square. To find the average power for 3 seconds, you have to calculate work done for 3 seconds. For that, you have to calculate the displacement for 3 seconds. So up to the same calculation is required for all the 3 questions. Now coming to the first part of the question. So displacement covered in first 3 seconds. Can be found by using the formula S equal half it square. If a body starts from rest and moves with constant acceleration, then displacement covered in time t is given by S equal half it square. T equal to here 3 seconds. So that comes out to be 9 by 2 meters. So work done by the agent for 3 seconds. Is equal to magnitude of the force applied by the agent into magnitude of the displacement into cos 0 degrees. Because the angle between F bar and S bar is 0 degrees. The force applied by the agent acts in the direction of the motion. Here a force applied by the agent is equal to nu s into mg in magnitude. So here nu s equal to 0.5. The weight mg of the block is given to be 100 newtons. Displacement for 3 seconds is 9 by 2 meters. So average power delivered by the agent for 3 seconds is equal to work done by the agent for 3 seconds divided by time interval. Work done by the agent for 3 seconds from this equation, you get 25 into 9 joules by 3 seconds. So that comes out as 75 watts is the answer for the first part of the question. Come on, you can copy down the solution of the problem. So in case you need some time to copy the solution of this value, you can take a pause and take your own time. Next, I am going to discuss the second part of the question. So in the second part of the question, you're asked to find the average power during the third second. The average power during the third second is equal to work done during the third second divided by time of motion for third second. Third second means it is the time interval between the two instants t equal to 3 seconds and t equal to 2 seconds. So to find the average power for third second, so you have to calculate work done during the third second, for which you have to find displacement covered during the third second. So displacement covered during the third second can be found by using the equation s equal half a t square. So body starts from rest and moves with constant acceleration. Then magnitude the displacement covered in time t is equal to s equal half a t square. Displacement covered in the third second is equal to displacement covered in 3 seconds minus displacement covered in 2 seconds. Displacement covered in 3 seconds can be found by substituting t equal to 3 seconds. Displacement covered in 2 seconds can be found by substituting t equal to 2 seconds. That means half a into 3 seconds square minus half a into 2 seconds square. I have taken half a common outside. So displacement covered during third second is equal to displacement covered in the first 3 seconds minus displacement covered in the first 2 seconds. Here acceleration is 1 meter per second square. So that is 5 by 2 meter. Can also calculate this displacement covered during the third second also by using this equation alternately. Displacement covered in nth second is equal to numerically equal to u plus a by 2 into 10 minus 1. To find displacement covered in the third second, you can put n equal to 3. Here a is 1. So displacement covered third second is numerically equal to 5 by 2. So work done during the third second is equal to force applied by the agent on the body multiplied by magnitude of the displacement during the third second. Magnitude of the force applied by the agent on the body, we have discussed earlier, is equal to F equal to nu mg. I mean nu F into mg. Here nu F is 0.5, 8 mg, the block is 100 newtons. So that is 50 newtons. So 50 newton into 5 by 2 meter. That is 125 joules. So the average power covered during the third second not average power during third second is different from average power for the first 3 seconds. Average power for the first 3 seconds we have calculated in the previous question, the first part of question. That is total work done in the first 3 seconds divided by time interval, that is 3 seconds. So average power during third second means it is equal to work done during third second. Work done during third second means work done in the time interval between the two instants t equal to 2 seconds and t equal to 3 seconds, which is equal to 125 joules. Divided by time interval for third second means 3 minus 2 seconds or 1 second. So that will be 125 watts. That's the answer for the second part of the question. So if you want to copy down the solution of this problem, you can take a pause and copy down the solution of the problem. Next, I am going to discuss the third part of the question. So next, I am going to discuss third part of the question. In the third part of the question, you are asked to find the instantaneous power at the end of third second. So to find the instantaneous power at the end of third second, you have to find the instantaneous velocity at the end of third second. So body starts from rest and moves with constant acceleration A, then measure the instantaneous velocity of time t is given by v equal to at. So at t equal to 3 seconds, v equal to a to t. T a is 1 meter per second square. To find the instantaneous velocity at the end of 3 seconds, you have to put t equal to 3 seconds. That will be 3 meter per second. So instantaneous power at the end of third second is equal to f bar dot v bar or fv cos theta. Here the angle between f bar and v bar is 0 degrees because the force applied by the agent acts in the direction of the velocity. F is the magnitude of force applied by the agent, which is equal to nu s into mg in magnitude. So here nu s is 0.58 mg is 100 newtons. Already we calculated the previous problem also f equal to 50 newtons, so that I directly can write f equal to 50 newtons. V 3 meter per second. So that will be 150 watts. That's the answer for the third part of the question. So in case you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So next I am going to discuss one more problem. Come on, look at the next problem, problem 3 on the screen. Block of weight 100 Newton, which is initially at rest on a horizontal floor, is lifted vertically upwards with a force of magnitude 120 Newton. Find the first part of the question. Average power delivered by the lifting agent in first 3 seconds. Second part of the question. Instantaneous power at the end of 3 seconds. So here I am going to this problem here. Solve this. G is equal to 10 meter per second square. In case you want to try it yourself, first you can take a pause and try it yourself. But I am going to discuss this problem. So come on, look at the solution of the problem. It is given that now the weight of the block is 100 newtons and G is 10 meter per second square. So you can substitute G equal to 10 meter per second square on the left side to find the mass of the block. So mass of the block you get 10 kg. Now the constant force applied on the block in the vertical upward direction given by capital F equal to 120 newtons. So only two external forces act on the block in opposite directions. In the first part of the question, you are asked to find the average power delivered by the lifting agent for the first 3 seconds. So you have to find the average power for first 3 seconds. For that you have to find displacement covered in the first 3 seconds. To find the displacement covered in the first 3 seconds, you have to find the magnitude of the acceleration of the block. To find the magnitude of the accelerated block, we have to apply Newton's second law. So here only two external forces are acting on the block in opposite directions, and magnitude of the lifting force in the upward direction is more than the magnitude of its weight mg. So resultant force on the block acts vertically upwards, and acceleration is also directed vertically upwards. Therefore, magnitude of the resultant force on the block equal to magnitude of the lifting force applied minus magnitude of its weight mg. From Newton's second law, magnitude of the resultant force of the block can be written as product of its mass and acceleration. So you can substitute all the given values. So you can substitute here F equal to 120 Newton on the left hand side, mg equal to 100 Newton on the left hand side. On the right side, mass m equal to 10 kg. So you get magnitude of the accelerator of the block at 2 meters per second square. The body starts from rest and moves with constant acceleration. Then magnitude of the displacement covered in time t is given by s equal to half at square. So to find the magnitude of the displacement in the first 3 seconds, you can substitute t equal to 3 seconds in the equation s equal to half at square. A is 2 meters per second square, t equal to 3 seconds. So magnitude of the displacement in the first 3 seconds will be 9 meters. So work done by the agent for first 3 seconds. That means up to this step, same calculation needed for both the parts of the question. This is the calculation which we are doing now, first part of the question. So work done by the agent in the first 3 seconds given by Fs cos theta. The force applied by the agent acts in the direction of the displacement of the body, so the angle theta between force and displacement is 0 degrees. The magnitude of force applied by the agent is 120 Newton. Magnitude of the displacement is 9 meters. So average power, the work done by the agent can denote it by W subscript A. So average power delivered by the agent in the first 3 seconds is equal to work done by the agent for the first 3 seconds divided by time interval. That is 120 into 9 joules by 3 seconds. So that will be 360 watts. That's the answer for the first part of the question. So those who want to copy down the solution, those who want to copy the solution of the problem, they can take a pause and copy the solution of the problem. Next, I am going to discuss the second part of the question. So in the second part of the question, you are asked to find instantaneous power at the end of 3 seconds. For that, you have to know the instantaneous velocity at the end of 3 seconds. The body starts from rest and moves with constant acceleration. Then magnitude of the instantaneous velocity of time t is given by v equal to at. So to find the instantaneous velocity at the end of 3 seconds, you have to substitute t equal to 3 seconds. We have already calculated the magnitude of acceleration of the body, which is equal to 2 meters per second square. So instantaneous velocity at the end of third second will be 6 meters per second. Therefore, instantaneous power at the end of 3 seconds or at the end of third second is equal to Fv cos theta. Here the angle theta between F bar and V bar is 0 degrees. Here V is the instantaneous velocity at the end of third second or at the end after t equal to 3 seconds. So we have already calculated the value of F is given in the problem 120 Newton. Magnitude of the instantaneous velocity is 6 meters per second. So you get 720 watts. you can observe that instantaneous velocity at the end of third second. Double the average, you can observe that instantaneous power at the end of third second. Double the average power for the first 3 seconds. Those who want to copy the solution, they can take a pause and then copy the solution of the problem.